All right, now we're going to take a look at hypothesis testing about a population variance. And again, what we're learning here is we're learning tools, and these are tools we could use in different situations. In the previous video, we saw how we could make inferences about a population variance and do interval estimation using chi-square. And I'm not even I'm not even 100% positive that I'm saying chi-square correctly, because I am new to statistics. Like, I took it as an undergrad. I've shared this story with you before, but just in case you're finding this video as a one-off, I took it as an undergrad. And I took it in graduate school, and quite honestly, I didn't really understand it. Even though I don't know what grade I got as an undergrad. It was a really bad experience. But as a graduate, I got an A. I got an A in the class. And so I must have understood it enough at the time to get an A. And then, you know, that was like 25 years ago. And now I've been asked to teach it again. And I'm excited to be here. And I'm enjoying it. And it's only now as the instructor that I'm really kind of going through it multiple times. It's taken me multiple times, taught it in the spring. Now I'm teaching it in the fall. And I'm making these lectures, but it's like literally the second time I've read this textbook, and second time I've been through these presentations, and second time I've done these exercises, and it's only now that I'm gaining yet even more clarity on it. So it's a hard thing to learn, and I'm not even sure I'm saying chi-square correctly. And so I looked this up here, and I'm showing you this because this is something you can do. And if you don't know how to pronounce something, you can look it up, and you can say chi-square definition, or you could do any word, like you could do sesquipedalian. Well, I'm going to actually do metaphysics, because that is something we've talked about. And
metaphysics.
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 Metaphysics. So, you can look it up and it'll tell you how to say it. So I'm not sure I'm saying it correctly. That's how new I am to statistics. And so I show you this so that you're empowered to, learn. And I really believe in the importance of all of us being human and being real with each other, and knowing what we know and being willing to share what we know, but also knowing what we don't know. And also being willing to share what we don't know. That's such an important quality, particularly when you get into the workforce, to say, hey, I know stuff. And this is what I know. I can learn stuff, so I can learn things I don't know. And this is what I don't know, and I'm totally willing to go out and learn it. And that level of sort of eager self-efficacy and eager humbleness. We'll call it eager humbleness. That eager humbleness where, yeah, I don't know stuff, but I could go learn it. I know how to learn it. I'll go look stuff up. I'll read it. Like, that's a really desirable quality. Right? Because then your employer is always going to know, or if you're starting a company, your employees will always know that you're going to be straight with them, and they'll be more comfortable being straight with you. So it's really important. So let's see if I'm pronouncing this correctly.
Chi-square.
Chi. I'm saying chi. I actually like chi better. Chi-square. Chi-square.
Chi-square.
Oh man, I'm kind of disappointed.
Chi-square.
Chi-square, relating to or denoting a statistical method assessing the goodness of fit between observed values and those expected theoretically. So observed versus expected. But we were also using it for this here, where we did interval estimation using chi-square. And now we're going to use it for hypothesis testing about a population variance. And you can see chi-square here. There's that formula, and we saw that formula in the previous video. So here's how that formula was right there. And then we also saw that formula right here. And so that formula right there. And then we also saw here the sampling distribution of n1 minus 1 over sample variance divided by population variance has a chi-square distribution whenever a simple random sample of size n is selected from normal population. I still like chi better. All right, so we're going to download this slide here. We're going to download it, and there it is. And then we're going to download this slide right here. We're going to download it. There it is. And not only are you learning, statistics, and not only are you learning how to learn, and you're learning how to be eager and humble, and that's a really empowered place to be. A lot of self-efficacy in there. Like, I don't know that right now, but I can figure it out. That's a lot of self-efficacy, really important. So not only are you learning statistics, not only are you learning eager humbleness, but you're also learning how to learn. And so if I give you a fish, I feed you for a day. But if I teach you to fish, I feed you for life. So here, chi-square. And I'm going to drop those two files here. So let me just go grab them. And here's my Finder. And I just downloaded those. I'm going to bring that over so it's right there. And there are those two files. I'm going to bring that over here. And I'm learning about chi-square in the slide with the graph that is approximating a bell curve. I'll just say that with the graph, there is a formula. There is a formula for chi-square. The other slide talks about, and let's go get that text, the sampling distribution of, here, let's do this. Let's see if we can get this here. Boop, 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 boop. As a chi-square distribution. I guess we'll copy that. We'll copy that and we'll put that here, and we'll put quotes and we'll boop and we'll do that. And the sound effect cracks me up a little bit. And we'll copy this and we'll put that there, and that's going to be here. Boop, and then we'll do this and we'll put that there, and we'll put this here, and we'll put that there, and then this has like a formula here, and my question is this: is that formula the formula that determines the graph? Also, my questions are this. Is that formula the formula that determines the graph? And also, is that graph the sampling distribution? And what is it? So it says the sampling distribution of this formula has a chi-square distribution whenever a simple random sample of size n is selected from a normal population. So let me see if that's my question. I'm learning about chi-square. In the slide with the graph, there's a formula for chi-square. The other slide talks about the sampling distribution of ... has a chi-square distribution whenever a simple random sample of size n is selected from a normal population. My questions are this: is that formula the formula that determines the graph? And also, is that graph the sampling distribution? And it determines those graphs because there's multiple one. And also, are those graphs the sampling distribution? The sampling distribution. There we go. Let's see what it says. And ChatGPT is great if you're using the paid version. The free version's not so much. Yeah, the formula shown in the slide is related to the chi-square distribution used to create the graphs. The graphs represent chi-square distributions with different degrees of freedom, and these distributions are used to model the variability in sample variance when you are estimating the population variance. The formula provided is the test statistic for chi-square distribution when performing inference on population variance based on sample data. Is the formula used to determine those graphs? Yes, the formula is used to calculate the chi-square statistic, which corresponds to different chi-square distributions depending on the degrees of freedom. These degrees of freedom are based on the sample size n. Are those graphs the sampling distribution? Yes, those graphs represent the chi-square sampling distribution for different degrees of freedom. Each curve corresponds to a different sample size as reflected by varying degrees of freedom. So to clarify, the formula is the test statistic, but the formula does not determine the shape of the graphs. Is that correct? Yes, that's correct. The formula is used as a test statistic for hypothesis testing or constructing confidence intervals, but it does not directly determine the shape of the chi-square distribution graphs. The shape of the chi-square distribution graphs is determined by the degrees of freedom, which are related to the sample size. The distribution changes shape as the degrees of freedom increase, becoming more symmetric and less skewed as the degrees of freedom rise. The test statistic formula is used in hypothesis tests and interval estimates involving variance. The graphs represent chi-square distribution for different degrees of freedom, which describes the behavior of the sampling distribution of the test statistic. Let me know if you need further clarification. What is the formula for determining those graphs? We'll see what it says to that. And if it gives me back that formula, the chi-square probability density function, there we go, that's what I was looking for. The graphs of the chi-square distributions are determined by the chi-square probability density function. We've heard that phrase before, which describes the shape of the chi-square distribution based on the degrees of freedom. The formula for chi-square probability density function is that big thing. Cool, so that's the test statistic. And I wasn't clear about that. The sampling distribution has a chi-square distribution. Because it's saying the sampling distribution of this has a chi-square, and I thought, well, is that what's making the formula? Whenever a simple random sample of size n, and it's like putting it here, like this determined that, so that kind of confused me. And but that just gives us the test statistic, and so the test statistic gives us, like, you know, the chi-square value and the p-value, and then also the p-value, and then also the chi-square value. That'd be it. And then I thought, did I draw that out when I was doing this one? So that's the textbook, and I'm just looking here to see if I drew that out. Let me pause this for a second, just look through these. Hold on one moment. Yeah, so I was just trying to remember if, like, in the because it's a lot, man. There's all these different tools, and I was trying to remember if in the previous, in this video, I actually had some sort of a drawing, because in the next two videos, I do drawings like this, where I do my little thing that I like to do. And in this video, we didn't do that. We just calculated the interval. All right, so a little bit of clarification there. And so now what we're going to do is, and we learned some good stuff, right? We're going to do hypothesis testing about a population variance. So we could do a left-tailed test. You could see left-tailed test. We could do a right-tailed test. You could see right-tailed test. We could do a two-tailed test, which is like an equality. And all of them are going to have the same test statistic. So as I flip between these, you can see it's using the same test statistic. And the test statistic, again, is that chi-square. You can see it's chi-square here. And we've used z, the z-test statistic. And so just so you have a little reminder of that. So here's like our z table, right? So let's bring that up and bring that over. So we use this as a test statistic. And then we also have used our t table. And I believe we've used this. And so here's our t table. And it's a bit of a blur, actually, because I've actually read ahead. And so I'm like, wait, did we talk about this already? Or is it just something I read ahead? And then here's chi-square. And so here we have cumulative probabilities for the standard normal distribution. That's our z. And we have t distribution and degrees of freedom. And then we have chi-square right here. So there are those right there. And so we've seen all of those as test statistics. And ultimately what we're going to do is stuff like this, where we have the probability, and then we have chi-square, critical value, and then here's our test statistic. And this is the critical value approach, and this is the p-value approach, and then you just evaluate it. And so we could do these different hypothesis tests. And so one of them would be, you know, here you have this notation. So variance with subscript 0 is the hypothesized value for the population variance. And so here you could say, here's the hypothesized value for the population variance right there. And then here you could do the same thing, but for a right-tailed test. And then there's a little bit more information there. They do their thing with the rejection rules. I don't really like memorizing those. I like thinking about it like this, where I draw this diagram and, you know, I'm doing this to 95% confidence level or whatever. And so this next one that we do, you'll see in the next video, I did all this with a notation. So 90% confidence level on this, that's my confidence coefficient. I have a level of significance of alpha is equal to 0.10, because your confidence level, confidence coefficient, and your alpha, your level of significance, have to add up to 1. So if this is 90%, that's got to be 10%. And this is a two-tailed test, so we divide alpha between each tail. So we get alpha over 2. Alpha over 2 gives us 5% in each tail. And then we do our p-value approach and our critical value approach. And this is my test statistic. And in this one, we're in the reject area. So we reject the null hypothesis that the two variances of two populations are not equal. We reject that they are equal. And so we're going to see that in the next one. But that's a really nice little diagram I did last night, just kind of showing you the terminology: confidence level, confidence coefficient, level of significance, alpha, is equal to 10, and then the p-value approach and the critical value approach, where in this one we're going to be using the f value. And so if you look, we've got the z table, we got the t table, we got the chi-square table, and then we also have the f table. And so that one's coming up in the next video. But that's just to illustrate that, here we're going to do hypothesis testing about a population variance. We could do a left-tailed, and then they have like their rejection rule. We could do a right-tailed, and they have their rejection rule. We could do a two-tailed, and they have their rejection rule. And all that is, I don't want to memorize it. I'd rather just draw these graphs. And so here's our example where we're actually going to see this in action. So St. Louis Metro Bus Company wants to promote an image of reliability by encouraging its drivers to maintain consistent schedules. The company specifies an arrival time variance of 4 minutes or less when arrival times are measured in minutes. Why don't they just do this, right? Like, that's where statisticians, I feel like, need to take some English classes, right? Like, isn't that simpler? We will conduct a hypothesis test with alpha is equal to 0.05 to determine whether the arrival population time variance is excessive. So we're going to do some sort of a less than here, right? Less than. And what we really want to test is, like, did it become too large? Like, we got our population, and so we're going to get a sample which will allow us to make inferences about the population. And so from that sample, we'll have 95% confidence that our sample, the estimate inferences it makes about the population, are accurate. And so if we go too high with our sample, we're going to reject it. Like, we were getting too far above 4. So it's going to be a right-tailed test. And if we get up into that right tail, the rejection area, so up here into this right tail, the rejection area, then, it was too far from 4, and we reject it. And so we're doing this with 95% confidence, which means our alpha here is 0.05. And if we go back to that terminology, this is a different example. That's our level of significance, our alpha, right? And our level of confidence, our confidence coefficient, will be 95%. And so already with our p-value, we could say 0.05. That's the probability from this point over to there. 5% of our data is over that way. And so, yeah, that's the probability. So I'm just checking that out here for a second. I'm just looking at that, and we'll see if that makes sense. I might have made an error in there. So if we look at the hypothesis, and then also when creating the hypothesis, right, the null hypothesis has to be the current state, no change, status quo, nothing changed. So we'll say that the current state is it's already less than or equal to 4. And if we reject that, the alternative hypothesis will be it's greater than 4. So if we're doing a right-tailed test, right, and a right-tailed test is going to look like this. Like, the population variance is going to be less than or equal to the hypothesized value for the population variance. And we're going to make that 4, right? So the population variance is less than or equal to 4. The population variance is greater than 4. And when we go look at this, we see the population variance is less than or equal to 4. And that's our null hypothesis, right? It's the current state, no change, status quo. All the bus drivers are bringing their wait times, the arrival time variance down to 4 minutes or less. Or the variance is greater than 4. And again, we're talking about variance. There's the mean, which is the average sort of arrival time, or the average arrival time. Like how, if this is the time you're supposed to arrive, what's the average? Like, are you a minute? Is a minute late? Is that your average? And then what's the variance on that, right? Because you could have an average of being 2 minutes late, and you could have a bunch of zeros, and then you could have like some 20s. And you have a lot of dispersion, a lot of variance, and still have an average of 2 minutes, depending upon it, right? So you want to know the variance of 4 minutes or less, right? So you can see how much variance you have there. So there's our hypothesis. And then when we conduct this test statistic, we put it into this formula here. And so our sample size is 24. And our sample variance is 4.9. And then the hypothesized, that D0 deal, right? So D subscript 0. So let me just go there. So here's our right-tailed test. And it's the sigma, the variance subscript 0. So variance subscript 0 is the hypothesized value for the population variance. So here's the hypothesized value for the population variance. It's 4. So we get chi-square of 2818. So let's open up our table and see if we can make sense from our table what we need to do. So I bring this table over here, And here's the table. And we have in this table, let's just make this bigger. I'll grab that, make that bigger, grab this, make that bigger, and then grab this and bring it over, and we'll just get this bigger. There we go. It's as big as I can get it. And we have n minus 1 degrees of freedom, and so that's 24 minus 1 is 23. So we're at right here, 23 degrees of freedom. And we want area in the upper tail to be 5%, right? So that's going to be our alpha up here, 5%. So we're at 23, and we have 5%, so that brings us to 35,172. And so here we've got, in our graph, we've got both our alpha, 0.05, for our p-value approach, and for our critical value approach, we're going to have 35.172. And so when we graph this, we have 35.172 for our critical value approach, and then we also have 0.05 here for our p-value approach, 0.05 for our p-value approach right there. And then when I come back over here and we look at this test statistic, we have 2818 as our test statistic for chi-squared. So if we look, where would 23 degrees of freedom right there. And if we look, where would 2818 fall? 28 is going to be between 14 and 32. So we're going to be between 0.9 and 0.1. So between 0.9 and 0.1. And so here we have 2818 is our test statistic. And then here we're going to be between 0.9 and 0.1, which is, I wrote here 14 and 32, which would be the test statistic, because I did this last night. Maybe I was a little tired. And really it's between 0.9 and 0.1. So that needs to be between 0.9 and 0.1. So I need to change that. And to change that, I kind of just want to print this, but I guess I'm going to redraw it. So hold on. All right, so I drew a new picture, so I'm just going to delete this picture here. So I select it, click on it. You can see the little sizing handles around the corner. That's when it's selected. And pop, that one goes away. And Command Z just to make sure that's the one I want to go away. Yeah, that's the incorrect one. And now I'm going to come over here and grab my new one. So that's my new one right there. I'm going to drag that out and drop it. And I'll go up here and do crop. I just took this picture with my phone and emailed it to myself. And that's my desk in the background, which I made 23 years ago. And made it by hand, man. I didn't cut the trees down, but I bought the lumber and put it all together. And it's beautiful. I love it. And so I cropped that picture just to make it look pretty. And then drag that up there just so we could see it a little bit larger. I think that's big enough. And then drag this down here so it goes full screen, and then bring this into the center. And I'm showing you this so you learn additional stuff, you know, like added value. No extra charge. You want extra toppings on your pizza with your education here? No extra charge. Pizza parlor, they're going to charge you for extra stuff. But here, you get it for free. All right, so here's this drawing. And I like this a lot better. So the p-value, so again, if we were to look at this image, and so there's the image, right? At 23 degrees of freedom, we had a test statistic of 2818, which is right between those chi-square values, which puts us between 0.9 and 0.1. So it's going to be closer to 0.1 just because we're closer to 32. We're at 28. So I mean, that might be like 0.12 or 0.14 or something. Sorry. That would be like 0.12 or 0.14 of this, but down here we're at 28, right? So we'll be closer to 10%. So we'll be like 12% or 14% up here. So anyhow, I put 0.9 to 0.1 here, which is greater than 0.01. And then our test statistic that we calculated is 2818, and the critical value is 35,172, and this is called the critical value approach, and this is the test statistic, and that's the critical value. Do we go past this value, or are we still under it? And this is the p-value approach. Do we go past this value, or are we still under it? In both cases, we're under it, so we do not reject our null hypothesis. And here it's the 95% confidence level or confidence coefficient, call it either one. And we're at alpha of 0.05, and that's called our level of significance. Our degrees of freedom, I didn't finish that, is 23. So that's our degrees of freedom, is this n minus 1, 24 minus 1. I just forgot to write that. So I guess I'll take another picture and add that in. I haven't crumpled up this paper yet. degrees of freedom is 23. And hold on one sec, you'll just see it all in action. All right, and just finish this out. Delete that, go back here, get the new one, and grab that, bring it down, and then crop it once more. And looks like I took it a little bit of an angle. That's right, that'll be good. And that'll be good. Oops, Command Z to undo that. I need to grab the black bar right there to bring it over. And bring this one up. Oh, not that one. This one, where is it? Come on, give me the black bar. There it is. That's what I want. And then bring this one over. That's what I want. And press Enter. And then just bring this up to this corner here. And then drag it down. And there it is, 23 degrees of freedom. Cool. So the book did it this way. That's how they explain it. But they get to the same thing, cannot reject. And that's the p-value approach. And then here's their diagram, which quite frankly is not super helpful to me. and then here's the critical value approach. And you also say cannot reject. But I much prefer my approach right here. That makes a lot of sense to me right there. The other stuff, not so much. Anyhow, find what works for you. Do it the way you do it. Just figure out how to do it. See you in the next video.